In the nature, a system with more energy is less stable. In other words, the lowest energy state corresponds to the most stable state of the system. So, every system tends to attain stability by losing energy. Let's see how the atoms attain the lowest energy and tend to be in a stable state. We know that the nature is associated with innumerable chemical reactions. It is a known fact that an atom is the smallest particle that takes part in a chemical reaction. Hence, most of the elements exist in a combined state in the form of molecules. The few elements which exist independently are noble gases. This is attributed to the stable electronic configuration and the minimum energy they possess. Hence, the atoms of other elements which do not have stable electronic configuration and the minimum energy combine with other atoms of elements to form molecules. Thus, these atoms attain stability by the means of bond formation. The process of bond formation is associated with the lowering of energy of the system. The attractive force which holds various atoms together in a molecule is called a chemical bond. COLLAGE and Lewis made an attempt to explain the chemical bond formation in terms of electrons. According to them, noble gases are chemically inert because they have stable electronic configuration. The stable electronic configuration is due to the presence of either 8 electrons in the outermost shell, called octet configuration, or 2 electrons in the first shell, called duplate configuration. Hence, they exist independently in atomic state. On the contrary, the remaining elements having less than 8 electrons in the outermost shell are chemically reactive. Hence, they combine with other atoms of elements by means of chemical bonds so as to attain stable octet. So, they do not exist independently but exist in combined states as molecules. Thus, the COLLAGE-Lewis approach provides an explanation for the requisite of formation of bonds. Later in 1916, COLLAGE and Lewis developed the electronic theory of valence or theory of chemical bonding to explain the chemical bond formation between the two atoms. According to electronic theory of valence, every atom tries to attain octet in its valence shell by losing or gaining or by sharing of electrons. This is known as the octet rule. Only valence electrons are responsible for the formation of chemical bond. Except valence electrons, the remaining part of the atom, that is the nucleus, with the inner shell electrons, is called kernel. Lewis proposed simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. As per Lewis symbols, the number of valence electrons of an element are represented as dots around the symbol. Let's look at the Lewis symbols of the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon as shown. The number of dots around the symbol gives the number of valence electrons. These valence electrons are useful to calculate the group valence of the element. The group valence of an element is equal to number of valence electrons of an element, or 8 minus the number of valence electrons. This is the significance of Lewis symbols. Now, let us look at the formation of ionic bond or electrovalent bond, which was explained by COLLAGE by considering the following facts. Halogens which are highly electronegative and alkali metals which are highly electropositive are separated by noble gases in the periodic table. Hence, halogens gain an electron, whereas alkali metals lose an electron to form negative and positive ions respectively. The positive ion and the negative ion thus formed attain octet configuration. The two oppositely charged ions approach each other and form an ionic bond or electrovalent bond. The electrostatic forces of attraction that holds the two oppositely charged ions together is known as the electrovalent bond. On the basis of these facts, let's explain the formation of sodium chloride. The electronic configuration of sodium is 2, 8, 1, whereas the electronic configuration of chlorine is 2, 8 and 7. When both sodium and chlorine combine together, sodium loses its one valence electron and forms positive ion, that is, sodium ion, whereas chlorine gains the one electron lost by sodium and forms the negative ion, that is, chloride ion. The sodium ion and the chloride ion attain the octet configuration of neon and argon respectively. These two oppositely charged ions approach each other and form sodium chloride. Due to the strong electrostatic forces of attraction between these oppositely charged ions, an ionic bond is said to be formed. Thus, sodium chloride is formed by the transfer of electrons from sodium to chlorine. The number of unit charges present on the ion is called electrovalence. In sodium chloride, sodium is assigned a positive electrovalence of 1, while chlorine is assigned a negative electrovalence of 1. Similarly, we can explain the formation of potassium chloride, calcium chloride, magnesium oxide, and other ionic compounds. On the basis of Cosell and Lewis' approach towards chemical bond, we can explain the factors that affect the formation of ionic bond. The formation of ionic bonds depends upon the following three key factors. First, the ease of formation of a cation. Second, the ease of formation of an anion. And finally, the arrangements of the positive and the negative ions in the ionic solid. Let us understand this by considering the formation of sodium chloride. In the formation of sodium chloride, sodium loses one electron and attains the configuration of its nearest noble gas, neon. The amount of energy required for the ionization of a neutral atom, which is sodium atom in this example, is called ionization enthalpy. It is always endothermic. Similarly, chlorine accepts one electron to attain the configuration of its nearest noble gas, argon. The amount of energy liberated for the gain of electrons by chlorine atom is said to be electron gain enthalpy. It is represented as delta EGH. It is defined as the enthalpy change when a gaseous atom gains an electron. Note that the electron gain enthalpy may be exothermic or endothermic. Thus, sodium forms a positive ion, that is a cation, whereas chlorine forms a negative ion, that is an anion. due to the strong electrostatic forces of attraction between these oppositely charged ions. They are held together to form sodium chloride. Now let us understand how ionization enthalpy and electron gain enthalpy affect the formation of an ionic bond. The ease of formation of a cation depends on the magnitude of the ionization enthalpy. Lower the ionization enthalpy, easier the removal of electron, and hence greater is the ease of formation of cation. Similarly, the ease of formation of an anion depends on the magnitude of the electron gain enthalpy. More negative is the electron gain enthalpy, greater is the ease of formation of the anion. Hence, we can conclude that lower the ionization enthalpy and higher the negative value of electron gain enthalpy, greater is the ease of formation of an ionic bond. The resultant ionic compound consists of regular and orderly arrangement of oppositely charged ions in three-dimensional region, held by strong electrostatic forces of attraction. This means that each cation is surrounded by a fixed number of anions and each anion is surrounded by a fixed number of cations. In a crystal of sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions as shown here. The difference in the crystal structures of different ionic compounds is attributed to the size of ions, their packing arrangements, and other factors. Finally, a requisite number of oppositely charged ions combine to form a crystal lattice. This process involves the liberation of energy. The higher the amount of the energy released, the greater the stability of the ionic compound. The stability of an ionic compound can be predicted by calculating the total enthalpy change in the process. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive. But still, the crystal structure is stabilized due to the energy released during the formation of the crystal lattice. For example, in the gaseous state, the ionization enthalpy for the formation of Na+ from sodium is plus 495.8 kJ per mole, while the electron gain enthalpy for the formation of a chlorine ion is minus 348.7 kJ per mole. The sum of the two, which is 147.1 kJ per mole, is positive. But this is compensated by the energy released during the formation of the crystal lattice of sodium chloride, which is minus 788 kJ per mole. The overall energy released is the sum of 495.8 minus 348.7 and minus 788, which results in minus 640.9 kilojoules per mole. Since energy is released in the process, it makes the crystal lattice more stable. Thus, the magnitude of energy released during the formation of crystal lattice, called lattice enthalpy, provides a measure for determination of the stability of the ionic compound. Thus, lattice enthalpy plays a vital role in the formation of ionic compounds. Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, The lattice enthalpy of sodium chloride is 788 kilojoules per mole. This means that the energy required for the separation of 1 mole of solid sodium chloride into 1 mole of gaseous sodium ion and 1 mole of chloride ion is 788 kilojoules per mole. Langmuir refined the Lewis postulates and introduced the term covalent bond. The bond formed by the mutual sharing of electrons between the combining atoms of the same or of different elements is called a covalent bond. During covalent bond formation, each atom tries to attain octet, that is, 8 electrons in its valence shell, or duplet 2 electrons in the first shell. The formation of covalent molecules can be understood from the Lewis dot structures. In the Lewis dot structures, the valence electrons of all the bonded atoms of a molecule are represented by dots. The following conditions are to be satisfied for the formation of a covalent bond in a molecule. Each of the bonded atom must contribute equal number of electrons to the shared pair. A bond is said to be formed when an electron pair is shared between the bonded atoms. All the bonded atoms must attain the nearest inert gas configuration as a result of sharing of electrons. Let us understand the formation of chlorine molecule by writing Lewis dot structure. The electronic configuration of a chlorine atom is neon 3s2 3p5. It has 7 electrons in its valence shell. Hence, it needs 1 more electron to attain the nearest inert gas configuration of argon. Therefore, each chlorine atom contributes 1 electron for sharing, and this electron pair is shared mutually by both the chlorine atoms. This shared electron pair joins 2 chlorine atoms together in the chlorine molecule. That is, if 1 electron pair or 2 electrons are shared between 2 bonded atoms, a single bond is said to be formed. Similarly, let us look at Lewis dot structures which depict the formation of covalent bonds in methane and carbon tetrachloride. Now, let us understand the formation of the oxygen molecule by writing the Lewis dot structure. The electronic configuration of oxygen atom is helium 2s2 2p4. It has 6 electrons in its valence shell. Hence, it needs 2 more electrons to attain octet. When 2 oxygen atoms approach each other, each of the oxygen atom contributes 2 electrons for sharing. Both the oxygen atoms mutually share these 2 electron pairs and attain the nearest octet configuration of neon. As the 4 electrons in 2 electron pairs are shared between 2 oxygen atoms, the 2 oxygen atoms are said to combine by a double bond in the oxygen molecule. Similarly, we can show the formation of carbon dioxide, ethylene, C2H4 molecules by Lewis dot structures as shown. Let us understand the formation of nitrogen molecule using Lewis dot structure. The electronic configuration of nitrogen atom is helium 2s2 2p3. It has 5 electrons in its valence shell and needs 3 more electrons to attain octet. When 2 nitrogen atoms approach each other, they mutually share 3 electron pairs and attain the nearest inert gas configuration of neon. As 6 electrons, that is, 3 electron pairs are shared between 2 nitrogen atoms, the two nitrogen atoms are said to join by a triple bond. Similarly, we can show the formation of acetylene, C2H2, and carbon monoxide molecule by Lewis dot structures as shown. Let us look at certain other important steps to be adopted while writing the Lewis dot structures for a molecule or an ion. In case a covalent molecule is formed between different atoms, then the atom with the least electronegativity is placed at the center, and other atoms will be placed at the terminal positions as shown here for a carbon dioxide molecule. Now, count the number of valence electrons available for bonding. In case of a molecule, count the total number of electrons present in the valence shell of all the bonded atoms. In case of ions, that is anions and cations, for each negative charge, add 1 electron to the total number of valence electrons, and for each positive charge, subtract 1 electron from the total number of valence electrons respectively. While writing a Lewis structure, it is always better to know the symbols for the respective bonded atoms or the combining atoms while you have to guess the skeletal structure of the molecule. This makes the distribution of the electrons between the bonded atoms easier. Among the valence electrons available for bonding, shared pair of electrons forms a single bond between two bonded atoms, and the remaining electron pairs present on the respective bonded atoms are either used for the formation of multiple bonds or remain as lone pairs. Finally, each atom should attain octet in its valence shell, except hydrogen, which attains the stable duplet configuration. Now let's see how to write the Lewis dot structure for carbonate ion by adopting the above-mentioned steps. First, let us calculate the total number of valence electrons in the carbonate ion shown here. The number of valence electrons in carbon is 4, whereas the number of valence electrons in oxygen is 6. As 3 oxygen atoms are present, the number of valence electrons in 3 oxygen atoms is equal to 18. As 2 negative charges are present on the carbonate ion, add 2 to the total number of valence electrons present in carbon and oxygen atoms. The total number of valence electrons here is 22. Hence, the total valence electrons in carbonate ion is 22 plus 2 equal to 24. In the carbonate ion, as carbon is less electronegative, it is placed at the center, whereas 3 oxygen atoms are placed around it at the terminal positions. The skeletal structure of carbonate ion is as shown. Now let us draw a single bond between the central carbon atom and each of the oxygen atoms. This, however, doesn't complete the octet on carbon, if the remaining 2 electrons on this oxygen remain as lone pair. Hence, a double bond between the carbon and the oxygen completes the octet. This results in the following Lewis dot structure. Now let's see how to write the Lewis dot structure for ammonium ion. First, let us calculate the total number of valence electrons. The number of valence electrons in nitrogen is 5, whereas the total number of valence electrons in 4 hydrogen atoms is 4. And as 1 positive charge is present on the ammonium ion, subtract 1 from the total number of valence electrons present in nitrogen and hydrogen respectively. That makes it 9. Hence, in the ammonium ion, the total number of valence electrons is 9 minus 1 equals 8. In the ammonium ion, nitrogen is placed at the center and the 4 hydrogen atoms are placed around it at the terminal positions. The skeletal structure of ammonium ion is as shown. When each hydrogen is bonded to nitrogen by a single bond, nitrogen attains octet and hydrogen attains duplet respectively, resulting in the shown Lewis structure. Let us now discuss about formal charge. In the case of monoatomic ions, the net charge belongs only to that particular atom. For example, chloride ion, oxide ion, sodium ion, magnesium ion, etc. In the case of polyatomic ions, the net charge is possessed by the ion as a whole and it does not belong to any particular atom. But we can assign a formal charge on each atom in the polyatomic ion. Formal charge is equal to the total number of valence electrons in the free atom minus total number of non-bonding electrons minus half of the total number of bonding electrons. While counting the electrons on the atom in a molecule, it is assumed that an atom owns 1 electron of each shared pair and 2 electrons of the lone pair. Let's calculate the formal charge on the oxygen atoms in the ozone molecule. In the ozone molecule, 3 oxygen atoms are present. Of these 3, 1 oxygen atom acts as a central atom. This is the Lewis structure of the ozone molecule. Let us number the 3 oxygen atoms as 1, 2, 3 respectively. Let us first calculate the formal charge on the first or central oxygen atom. The formal charge on it is equal to 6 minus 2 minus half multiplied by 6, which is equal to plus 1. The formal charge on the second or doubly bonded oxygen atom is 6 minus 4 minus half multiplied by 4, which is equal to 0. The formal charge on the third or single bonded carbon atom is 6 minus 6 minus half multiplied by 2, which is equal to minus 1. Remember that the formal charges do not show the real charge separation within the molecule. Formal charges are useful to predict the most stable structure among the possible Lewis dot structures of the compound. Now let's move on to limitations of Lewis theory. Though octet rule is simple, it is not applicable to all the molecules. It is mainly applicable to organic compounds and compounds formed by second period elements such as methane and water. Octet rule is not applicable for the molecules containing odd electrons. For example, there are only 7 electrons around nitrogen in nitric oxide. Octet rule is not applicable for the molecules in which the central atom has less than 8 electrons. That is, contracted octet. This is observed in the compounds or molecules in which the central atom in its elemental state possesses less than 4 electrons in its valence shell. For example, lithium in lithium chloride, boron in boron trifluoride and boron trichloride, beryllium in beryllium chloride, aluminium in aluminium chloride don't possess octet. The atoms of the elements that belong to the third period and beyond the third period possess 3d orbitals available for bonding. Hence, most of the compounds formed from them possess more than 8 electrons around their central atoms. This is called expanded octet. Hence, the octet rule is not applicable for the molecules such as phosphorus pentachloride and sulfur hexafluoride, etc. In phosphorus pentachloride, phosphorus, the central atom has 10 electrons in its valence shell. In sulfur hexafluoride, sulfur is the central atom and it has 12 electrons in its valence shell. We know that each atom gets stability due to octet in its valence shell. But some elements like krypton and xenon forms compounds in spite of having octet in the valence shell, such as xenon difluoride, xenon oxydifluoride, krypton difluoride, etc. The octet rule couldn't explain this anomaly. Lewis theory does not explain about the shapes of the molecules. It also does not explain about the relative stability of the molecules as well as the energies of the molecule. Drawing the atomic structures of complex compounds with bonds is difficult. To overcome this, Lewis established an easy way to represent bonds within molecules and ions. He created it as per the shared pair of electrons and the octet rule. In his method, electrons are drawn as dots and the bonding of a pair of electrons is represented by a line. Therefore, it is also known as the electron dot structure. The Lewis structure for an atom is the chemical symbol for the atom, surrounded by as many number of dots as the number of valence electrons in it. For an ion of an element, we first need to draw the chemical symbol for the element surrounded by the number of valence electrons present in the ion. Then, the whole structure is placed within square brackets, with the superscript indicating the charge on the ion. The charge of the ion is the number of electrons gained or lost. To draw the Lewis structure for a molecule, first draw the atoms and join them with lines so that for each atom, the total number of valence electrons becomes 8. To draw the Lewis structure for compounds, first, the unit of the negative or positive charge should be deducted from the total number of valence electrons of the compound. The remaining number of valence electrons should be distributed as the bonding pairs of electrons. For example, a carbonate ion has 2 negatively charged units. The number of valence electrons in a carbonate ion is the sum of valence electrons of 3 oxygen atoms and the valence electrons of the carbon atom. That is 22. Therefore, the number of electrons to be distributed in a carbonate ion will be 22 minus negative 2, that is 24. In the Lewis structure, the least electronegative atom occupies the central position, which is carbon here. Now, when 24 electrons are distributed among 3 oxygen and 1 carbon atoms, it looks like this. After assigning electrons, the remaining electrons are utilized for multiple bonds or remain as lone pairs. We will replace each pair of bonded electrons with a line. Notice that the total number of valence electrons becomes 8 for each atom. With the sharing of valence electrons for the full octet in each atom, the Lewis structure involves the octet rule. However, there are some molecules in nature that do not follow the octet rule. In some molecules, the number of electrons surrounding the central atom is less than 8. For example, beryllium hydride and boron trichloride have 2 and 3 pairs of electrons respectively surrounding the central atom. In molecules with an odd number of electrons, such as nitric oxide, the octet rule is not satisfied. The octet rule also does not apply to the molecules with expanded octets. Though the octet rule is based on the inertness of noble gases, some noble gases such as xenon and krypton react with other elements and form compounds. The octet theory also does not explain the shapes of molecules and energies of orbitals. However, the molecules that do not follow the octet rule can still be represented by the Lewis electron dot structure. Therefore, though the Lewis structure involves the octet rule, it is not limited to the octet rule. However, in case of polyatomic molecules, there can be more than one possible Lewis structures for a molecule. To determine the best possible Lewis structure for a molecule, we need to find out the structure with the lowest energy from a number of possible Lewis structures. The lowest energy structure is the structure with the smallest formal charge on the atom. Formal charge is the charge assigned to an atom in a molecule, assuming that electrons are shared equally between atoms in a chemical bond. For the correct Lewis structure, it should be other than 0. The formal charge can be expressed as the difference between the number of electrons present in that atom in its isolated state and the number of electrons assigned to the atom in the Lewis structure. For example, in a phosphine molecule, the number of valence electrons in the phosphorus atom is 5, and the number of lone pairs is 2. There are 6 shared electrons among 3 hydrogen atoms and 1 phosphorus atom. Therefore, the formal charge is 5 minus 2, minus half of 6, which is 3. This gives us the formal charge as 0. The Lewis structure and formal charges are applicable only to the molecules formed by covalent bonding. Let's understand what a covalent bond is. In 1919, with the help of Lewis postulates, Langmuir brought in the term covalent bond to define a bonding pattern where the electrons are not transferred. In covalent bonding, atoms share electrons so that the number of valence electrons in each atom becomes 8. For hydrogen, it is 2. Here, the nuclei of both the atoms keep attracting the shared electrons and do not give away any electron completely, unlike ionic bonding. For example, in a water molecule, one oxygen atom shares valence electrons with 2 hydrogen atoms. In this way, the valence electrons in an oxygen atom will be 8, and thus, oxygen gets the stable status of its nearest noble gas, neon. On the other hand, by sharing 1 electron of oxygen each, the hydrogen atoms will have 2 valence electrons each. It will get the configuration of helium. When 2 atoms share 1 electron pair, they form a single covalent bond. For example, the fluorine molecule. When 2 atoms share more than 1 electron pair, they form multiple bonds. In the ethylene molecule, the 2 carbon atoms share 2 pairs of electrons and a double bond is formed between the 2 atoms. Nitrogen molecules form triple bonds. The factors that affect chemical bonds are known as bond parameters. Some such factors are bond length, bond order, bond angle, and bond enthalpy. Let's look at each of these factors. Bond length is the distance between the nuclei of the atoms that are bonded together. It is directly related to the radius of each atom in the bonded pair. In a covalent bond, the radius of each atom forming the bond is called the covalent radius of the atom. In a molecule containing similar atoms, the size of the atoms is the same. Hence, their radii will be the same. In such cases, the covalent radius is half the internuclear distance between the bonded atoms. Another type of radii between atoms is the van der Waals radius. It was calculated by van der Waals and provides the overall size of an atom, including its non-bounded valence shell. It is given as half the distance between two similar atoms in separate molecules in a solid. Some of the methods used to measure bond lengths are spectroscopy, X-ray diffraction, and electron diffraction. The bond length between carbon atoms in an ethane molecule is calculated to be 1.54 angstrom units. The carbon-to-carbon bond length in ethylene is 1.33 angstrom units, while in acetylene it is 1.20 angstrom units. This difference in bond length leads us to our next parameter, bond order. The number of chemical bonds between a pair of atoms in a molecule is called the bond order of the molecule. Bond orders can be calculated from Lewis structures. For example, in ethane, two carbon atoms share one pair of electrons. Therefore, the bond order is said to be 1. In ethylene, two carbon atoms share two pairs of electrons. Therefore, the bond order is said to be 2. And in acetylene, two carbon atoms share 3 pairs of electrons. Therefore, the bond order is said to be 3. Now, if you observe the bond order and the bond length of these molecules together, you will notice that they are inversely proportional to each other. This is because as the number of shared pairs of electron goes on increasing, the distance between the two nuclei forming the bonds goes on decreasing. From the Lewis dot structure, we get the sequence of atoms in a molecule. But what about its structure? For this, we need to look at the next bond parameter, bond angle. It helps us create a three-dimensional structure of the molecule around the central atom. In a molecule, the angle between the orbitals present around the central atom is called the bond angle. In a methane molecule, there are 1 carbon and 4 hydrogen atoms. the bond angle of methane is 109 degrees and 28 minutes. It means that the angle between any two bonds that are formed between a carbon atom and the hydrogen atoms is 109 degrees and 28 minutes. Usually, when the bond angle is 90 degrees, the shape of the molecule is octahedral. When the bond angle is 180 degrees, the shape of the molecule is linear. Similarly, when the bond angle is 120 degrees, the shape of molecule is trigonal planar. Bond angles are measured using spectroscopic methods. Another bond parameter, bond enthalpy, is defined as the amount of energy required to break one chemical bond between two gaseous atoms in a molecule. It is expressed in kilojoules per mole. For example, the energy required to break the bond between the two atoms of a hydrogen molecule is 435.8 kilojoules per mole. When a molecule is made of more than two atoms, it consists of more than one bond. In such cases, the bond enthalpy for each bond may be different. Hence, the average of all the bond enthalpies is taken as the bond enthalpy of that molecule. Bond enthalpy is inversely proportional to bond length. This means the shorter a bond between two atoms, the more energy it takes to break it. Does not explain the shapes of molecules. In 1940, this drawback led Sedgwick and Powell to come up with a theory to determine the shape of a molecule. The shape of the molecule is based on the number, type, or extent of repulsions between electron pairs present in the valence shell around the central atom respectively. This theory is named as valence shell electron pair repulsion theory, or the VSEPR theory. It was further developed and redefined by Gillespie and Nyholm in 1957. The valence electron pairs surrounding the central atom in a molecule mutually repel with each other. Thus, these electron pairs surrounding the central atom arrange themselves in space in such a way to minimize the repulsions, giving the molecule a definite geometry. The molecules in which the central atom is surrounded with only bond pairs, then it is said to possess definite geometry, as in case of BF3. As the electron pair is a negatively charged cloud, the bonded atoms move apart to minimize repulsions between the electron pairs. To minimize the repulsion, the distance between the atoms has to be maximum. To attain the maximum distance between the bonded atoms, imagine the valence shell to be a sphere and the electron pairs located on its surface at maximum distance from each other. The shape of a molecule depends upon the number of valence electron pairs and their arrangement around the central atom. The geometry of a molecule, in which the central atom does not have a lone pair of electrons, will be regular without any distortion. For example, the shape of a molecule with two bonded electron pairs around the central atom will be linear, with a bond angle of 180 degrees. The shape of a molecule with three bonded electron pairs around the central atom will be trigonal planar, with a bond angle of 120 degrees, and so on. In a methane molecule, 4 hydrogen atoms are bonded to one central carbon atom. Since the electron pairs have the same charge, they repel each other and try to stay as far away from each other as possible. As a result, all the 4 hydrogen atoms arrange at 4 corners of a tetrahedron, lying at equal distances away from each other. Hence, methane has tetrahedral shape. In the methane tetrahedron, the bond angle is 109 degrees 28 minutes. However, the geometry of the molecules gets distorted due to the presence of lone pair of electrons. Unlike bonded pairs that are shared between 2 atoms, the lone pairs of electrons are localized on the central atom. Due to this, they occupy more space, which results in greater repulsion. Thus, the geometry of the molecules with lone pair of electrons differ from the expected or regular geometry of the molecules having only bond pairs. In a molecule, the repulsion between lone pairs of electrons is always maximum. Thus, we can say that the repulsion between 2 lone pairs of electrons is more than that of a lone pair bond pair, which is greater than that of 2 bonded pairs. Assume a multiple bond to be a single electron pair. Therefore, the presence of multiple bonds will not affect the shape of a molecule. Now, let's analyze the shapes of some molecules with reference to their valence electron pairs. In ammonia, the central nitrogen atom has 3 bond pairs of electrons and 1 lone pair of electrons. The ideal geometry of the molecule with 4 pairs of electrons would be tetrahedral. However, the lone pair of electrons repulses the NH bonded electron pairs, thus reducing their bond angle to 107 degrees and giving the molecule a pyramidal shape. In a water molecule, the central oxygen atom has 4 bonded pair of electrons and 2 lone pair of electrons. We have seen that repulsion between lone pair, and lone pair bond pair is more than bond pair, bond pair. Thus, the 2 lone pairs on central oxygen atom makes the molecule to distort from its regular geometry to bend or V-shape, making a bond angle of 104.5 degrees. A sulfur tetrafluoride molecule is seesaw-shaped as its bond angles are at an angle of 101 and 173 degrees. Due to the lone pair of electrons present on its central atom. The chlorine trifluoride molecule is T-shaped and its bond angle is 87 degrees and 40 minutes, and the molecule shape is distorted due to the 2 lone pair of electrons on central chlorine atom. In a molecule of bromine pentafluoride, the central atom bromine has 5 bonded pair of electrons and 1 lone pair of electrons. Therefore, the geometry of the molecule is distorted, octahedral or square pyramidal. It is due to the presence of a lone pair of electrons on central bromine atom. In a molecule of xenon tetrafluoride, the central xenon atom is surrounded by 4 bonded pairs of electrons and 2 lone pairs of electrons. The geometry of the molecule is distorted. It is square planar from the regular octahedral geometry. It is due to the presence of 2 lone pairs of electrons on its central xenon atom. Approach to chemical bonding helps us to write the structure of molecules. It suffers from certain drawbacks. These drawbacks are: it fails to explain the formation of a chemical bond. It does not give the reason for the difference in bond dissociation energy and bond lengths in molecules like hydrogen and fluorine, although in both the cases a single covalent bond is formed. It also fails to give any idea about the shapes of the polyatomic molecules. The VSEPR theory, on the other hand, gives the geometry of the simple molecules but fails to explain their formation. To overcome these limitations, the valence bond theory and the molecular orbital theory, which are based on quantum mechanics, are introduced. The valence bond theory was introduced by Heitler and London and was developed further by Pauling and Slater. It explains the formation of covalent bonds. According to this theory, a covalent bond is formed when a pure valence atomic orbital of one atom overlaps with pure valence atomic orbital of another atom. Each of the overlapping orbitals contains the unpaired electron of opposite spin. The electron pair is shared by both the atoms. The strongest bond is formed when the orbitals of the 2 atoms overlap to the maximum extent. Let's explain the formation of hydrogen molecule on the basis of this theory. Consider 2 hydrogen atoms, A and B, approaching each other. Let us label their nuclei as Na and Nb and the electrons present in them as Ea and Eb. Now, as these 2 atoms come closer, forces of attraction as well as repulsion begin to operate. The force of attraction arises between the nucleus of one atom and its own electron, that is, between Na and Ea, and between Nb and Eb, and the nucleus of one atom and electron of another atom, that is, between Na and Eb, and between Nb and Ea. Simultaneously, repulsive forces also arise between the 2 electrons Ea and Eb, and the 2 nuclei Na and Nb. Experimentally, it is found that the magnitude of the new attractive forces is more than that of the new repulsive forces. As a result, the potential energy decreases as the 2 hydrogen atoms approach each other. Ultimately, a stage is reached where the nuclei remains at an optimum distance, such that the net force of attraction balances the net force of repulsion. At this stage, the system acquires minimum energy, and the 2 hydrogen atoms are said to be bonded to form a stable molecule. If we try to bring these atoms still closer, then the repulsive forces start overpowering the attractive forces. Consequently, energy of the system increases, causing instability to the system. As energy is released during the formation of the bond between the 2 hydrogen atoms, we can say that the hydrogen molecule is more stable than the isolated 2 hydrogen atoms. The energy so released is called the bond enthalpy, which corresponds to the minimum as shown in the figure. It is important to note that the same amount of energy is required to dissociate one mole of hydrogen molecule. Another example is the formation of a hydrogen chloride molecule. Here, when hydrogen atom approaches chlorine atom, a bond is formed due to the overlapping of s and p orbitals. The overlap can be positive, negative, or zero depending on the properties of the respective overlapping orbitals. Based on the overlapping of orbitals, two types of covalent bonds are formed. These are known as sigma and pi bonds. Sigma bonds are formed by the end-to-end overlap of atomic orbitals along the internuclear axis, known as a head-on or axial overlap. There are three types of head-on overlaps that form sigma bonds. They are SS overlap, SP overlap, and PP overlap. SS overlapping takes place when two half-filled s orbitals overlap along the internuclear axis. SP overlapping takes place when the half-filled s orbital of one atom overlapped with the half-filled p orbital of another atom along the internuclear axis. PP overlapping takes place between two half-filled p orbitals of two atoms along the internuclear axis. A pi bond is formed when atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The pi orbitals formed due to the sidewise overlap consists of two saucer-type charged clouds above and below the plane of the participating atoms. Pi bonds can be formed in addition to a sigma bond between two atoms and are always present in molecules with multiple bonds. The overlapping of orbitals extends to a larger area in sigma bonds than pi bonds. Therefore, sigma bonds are stronger than pi bonds. The overlap criterion of orbitals applies equally to both diatomic molecules and polyatomic molecules. However, the valence bond theory fails to determine the actual shapes of the polyatomic molecules, such as methane, ammonia, and water, which are tetrahedral, pyramidal, and bent respectively. Let us explain the above limitation by considering methane molecule. In methane, the central atom carbon has the configuration of 1s2, 2s2, 2px1, 2py1. In its excited state, the configuration becomes 1s2, 2s1, 2px1, 2py1, 2pz1. The four atomic orbitals of carbon, each with an unpaired electron, overlaps with four singly occupied 1s orbitals of the hydrogen atoms to form four CH bonds. We know that p orbitals lie perpendicular to each other. Hence, the three CH bonds in methane molecule are expected to be oriented at 90 degrees to one another. The two s and 1s orbitals of carbon and hydrogen can overlap in any direction, since they are spherically symmetrical. Thus, the direction of the fourth bond cannot be ascertained. This means that all the four CH bonds in methane are not identical. But experimentally it is observed that all the four bonds are exactly identical in all aspects and are oriented at a bond angle of 109.5 degrees. Similarly, valence bond theory cannot account for the correct bond angles in water and ammonia. While valence bond theory predicts to have a bond angle of 90 degrees in them, the experimental result suggests to have bond angles of 104.5 degrees and 107 degrees respectively. Thus, it can be seen that the valence bond theory fails to account for the actual shape of polyatomic molecules. Scientists observed that some molecular structures found in nature could not be scientifically explained with the help of the existing understanding of atomic orbitals. Pauling introduced the concept of the hybridization of atomic orbitals to explain the existence of such molecules. During hybridization, atomic orbitals of slightly differing energies redistribute to form a new set of orbitals with equivalent energies. The number of hybridized orbitals formed is equal to the number of atomic orbitals participating in the process. These hybrid orbitals align themselves in space such that there is minimum repulsion between the electron pairs. Because of this, the bonds formed by hybrid orbitals are more stable as compared to those formed by pure atomic orbitals. The phenomenon of hybridization is observed in the atomic orbitals s, p and d. Their possible combinations are sp, sp2, sp3, sp3d and sp3d2. Now let's study each combination in detail. In sp hybridization, one s orbital combines with one p orbital to form two equivalent sp hybrid orbitals. The hybrid sp orbital shows 50% characteristics of the s orbital and 50% characteristics of the p orbital. The hybrid orbital has a large positive lobe and a very small negative lobe. The hybrid orbitals are oriented in opposite directions, forming an angle of 180 degrees with each other. During bond formation, they provide maximum overlapping areas, making the bonds stronger and giving the molecule its linear structure. Some compounds whose central atom displays sp hybridization are BeCl2 and C2H2. In sp2 hybridization, one s orbital combines with two p orbitals to form three equivalent sp2 hybrid orbitals. They have a trigonal planar arrangement, and the angle between two orbitals is 120 degrees. Some compounds whose central atom displays sp2 hybridization are BeCl3 and C2H4. In sp3 hybridization, one s orbital combines with all the three p orbitals to form four equivalent sp3 hybrid orbitals. Each hybrid sp3 orbital displays 25% s orbital characteristics and 75% p orbital characteristics. They have a tetrahedral arrangement, and the angle between two orbitals is 109.5 degrees. Some compounds whose central atom displays sp3 hybridization are CH4 and C2H6. The hybridization of elements containing d orbitals leads to three distinct hybridized shapes formed by the mixing of s, p and d orbitals. They are dsp2, sp3d and sp3d2. Of these, we will study sp3d and sp3d2 hybrid orbitals closely. The energy of 3d orbitals is not only comparable to 3s and 3p, but also comparable to 4s and 4p. Therefore, the hybridization of d orbitals either involves the 3s, 3p and 3d orbitals, or the 3d, 4s and 4p orbitals. In sp3d hybridization, one s orbital, 3p orbitals and one d orbital combine to form 5 sp3d hybrid orbitals of equivalent energy. They have a trigonal bipyramidal arrangement, which leads to the formation of two different sets of angles between orbitals. 3 of the hybrid orbitals lie in one plane, making an angle of 120 degrees with each other. This plane is called the equatorial plane, and the bonds formed by them are called equatorial bonds. The remaining two orbitals arrange themselves above and below the equatorial plane, forming an angle of 90 degrees with the orbitals on the equatorial plane. The bonds formed by these two orbitals are called axial bonds. The axial bonds are repulsed by the equatorial bonds, causing them to be longer and weaker than the equatorial bonds. Ultimately, this makes molecules with sp3d hybridization more reactive. The central atom, phosphorus, in the compound PCl5 displays sp3d hybridization. In sp3d2 hybridization, one s orbital, 3p orbitals and 2 d orbitals combine to form 6 sp3d2 hybrid orbitals of equivalent energy. They have an octahedral arrangement and a bond angle of 90 degrees between the orbitals. The central atom, sulfur, in the compound SF6 displays sp3d2 hybridization. Thus, we can observe that the phenomenon of hybridization explains the characteristic geometrical shapes of polyatomic molecules. Electrons are present in orbitals of differing energy levels, such as 1s, 2s, 2p, and so on. They represent the probability of finding electrons around an atom. This observation led scientists F. Hunt and R. S. Millikan to develop the molecular orbital theory, which postulates that electrons in a molecule similarly exist in different orbitals, giving the probability of their presence around a molecule. However, for atomic orbitals to combine and form molecular orbitals, they must have similar energy levels and symmetrical molecular axes. This means that even though 2px of one atom has energy equal to 2py of another atom, they won't combine as they don't have the same symmetry. The number of molecular orbitals formed is equal to the number of atomic orbitals in the atoms forming the bond. Electron distribution in molecular orbitals takes place as per the Aufbau principle and obeys Pauli's exclusion principle and Hund's rule. The electrons in an atom are influenced by only one nucleus, forming monocentric atomic orbitals. However, the electrons distributed in molecular orbitals are influenced by the nuclei of all the atoms forming the molecule, causing the formation of polycentric molecular orbitals. In an atom, the electrons present in the atomic orbitals are represented using the Schrödinger wave equation of wave mechanics by the wave function y, which gives the amplitude of the electron wave. However, the Schrödinger wave equation cannot be used for molecules, and hence a new method called the linear combination of atomic orbitals, LCAO, was developed. To understand this method, let's consider the hydrogen molecule made up of two hydrogen atoms, A and B. At ground state, each hydrogen atom has one electron in the 1s orbital. Let's represent their wave function as psi A and psi B. Now, there are two ways to add the wave functions. One is when these wave functions are in phase, either both plus or both minus. And the other is when the two wave functions are out of phase, one plus and the other minus. When the two electron waves are in phase, they form the bonding molecular orbitals. Here, the electron density is between the two nuclei. The electrons tend to hold the nuclei together, thus stabilizing the molecule. Therefore, we conclude that a bonding molecular orbital always possesses lower energy than either of the atomic orbitals that have combined to form it. When the two electron waves are out of phase, they form antibonding molecular orbitals. Here, the electron density between the two nuclei is reduced such that it is zero at the nodal plane. This leads to mutual repulsion of the electrons. As the energy of the mutual repulsion is more than the attraction between the electrons and the nuclei, the net orbital energy increases. Thus, the energy of the antibonding orbital is raised above the energy of the parent atomic orbitals that have combined, and the energy of the bonding orbital is lowered than the parent orbitals. However, the total energy of the two molecular orbitals remains the same as that of the two original atomic orbitals. Molecular orbitals are obtained by combining the atomic orbitals of the atoms in a molecule. For example, in the hydrogen molecule, each atom has one electron in its 1s orbitals. These two 1s orbitals come together to form two molecular orbitals. One of these two molecular orbitals is formed due to the constructive interference of the two 1s wave functions, and the other is formed due to the destructive interference of the two 1s wave functions. The molecular orbital formed due to constructive interference is called a bonding molecular orbital, as the electrons belonging to it are placed between the two nuclei. This stabilizes the molecule The molecular orbital formed due to destructive interference is called an anti-bonding or sigma star molecular orbital, as the electrons belonging to it are placed away from the region between the two nuclei. This increases their energy, thus making the molecule less stable. Just as in atoms, electrons in a molecule too first occupy lower energy levels. Thus, we find that the 2 electrons of the hydrogen molecule first occupy the sigma bonding molecular orbital. This lowers the overall energy of the molecule compared to the isolated hydrogen atoms. Molecular orbitals not only help us determine the stability of molecules such as hydrogen, they also help us understand why certain molecules such as the helium diatomic molecule do not exist in nature. You see, helium atom has 2 electrons in its 1s orbital. When 2 helium atoms come together to form a molecule, the 4 electrons would be distributed across both sigma bonding and sigma star anti-bonding molecular orbitals. The energy of the sigma bonding molecular orbital will be low. However, the energy of the sigma star anti-bonding molecular orbital will be considerably higher. Thus, the overall energy of a helium diatomic molecule will be the same as that of 2 helium atoms. So, there will be nothing holding them together. Hence, the helium diatomic molecule does not exist. 4 molecules formed by atoms containing more than 2 electrons. We will only consider the molecular orbitals formed by their valence shell and not the ones formed by their core orbitals to understand their stability. Now let's study the molecular orbitals formed in an oxygen diatomic molecule. Oxygen has the atomic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. When 2 oxygen atoms come together, their 1s2 atomic orbitals combine to form 2 molecular orbitals. Their electrons are concentrated along the bond axis. Hence, they are called sigma 1s bonding and sigma star 1s anti-bonding molecular orbitals. The 2s orbitals combine to form sigma 2s bonding and sigma star 2s anti-bonding molecular orbitals. Two 2pz orbitals too combine head-on to form sigma 2p bonding and sigma star 2p anti-bonding molecular orbitals. However, the 2px and 2py orbitals combine sideways to form a p orbital shaped bond with the electrons concentrated either above or below the bond axis. Hence, these molecular orbitals are called pi orbitals. The 2px atomic orbitals combine to form pi x bonding and pi star x antibonding molecular orbitals, whereas the 2py atomic orbitals combine to form pi y bonding and pi star y antibonding molecular orbitals. As the energies of the 2px and 2py atomic orbitals are the same, the energies of pi x bonding, pi y bonding molecular orbitals and pi x star antibonding, pi y star antibonding molecular orbitals are the same. Thus, the interaction between the valence shells of two oxygen atoms leads to the formation of 8 molecular orbitals: sigma 2s, sigma star 2s, sigma 2p, sigma star 2p, pi x, pi y, pi star x, and pi star y. Due to the difference between 2s and 2p atomic orbitals, the resultant molecular orbitals sigma 2s and sigma star 2s lie below the other 6 orbitals. Due to the head-on bonding between 2pz atomic orbitals, the interaction between them is stronger than the 2px and 2py orbitals. As a result, the sigma 2p orbital lies below the pi x and pi y orbitals, and the sigma star 2p orbital lies above the pi star x and pi star y orbitals. While this sequence of molecular orbitals is accurate for molecules such as oxygen and fluorine, but not for other elements such as boron, carbon, and nitrogen, the molecular orbital's energy sequence is slightly different. This is because of the interaction between the electrons of the 2s atomic orbitals of one atom with the electrons of the 2pz atomic orbitals of another atom due to their relatively similar energy levels. In these molecules, the energy level sequence is sigma 2s, followed by sigma star 2s, followed by pi x and pi y that are at the same energy levels, followed by sigma 2p, followed by pi star x, pi star y, and finally sigma star 2p. As we know, the number of bonds between a pair of atoms is called the bond order. In terms of molecular orbitals, to calculate the bond order, we assume that 2 electrons in a bonding molecular orbital form one bond, and that 2 electrons in antibonding molecular orbitals cancel the effect of one bond. Thus, we can calculate the bond order in an oxygen molecule using the formula bond order is equal to number of electrons in the bonding molecular orbitals minus number of electrons in the antibonding molecular orbitals divided by 2. Now, in oxygen, the number of electrons in the bonding orbitals is 8, and the number of electrons in the antibonding orbitals is 4. So, adding these values to the equation, we get the bond order as 2. As we know, when electrons in an atom or molecule are paired, as in nitrogen, they form a dimagnetic atom or molecule. And when the electrons in an atom or molecule are not paired, as in oxygen, they form a paramagnetic atom or molecule. In this way, the molecular orbital model helps us understand the structure and properties of molecules. Hydrogen molecule, which is formed by the combination of 2 hydrogen atoms. You know that a hydrogen atom has just 1 electron, and it is placed in the 1s orbital. So, a hydrogen molecule will have 2 electrons that are present in the sigma 1s molecular orbital. The electronic configuration of a hydrogen molecule is sigma 1s2. Let us calculate the bond order of hydrogen molecule. As the number of electrons present in the bonding orbital is 2, and as no electrons are present in antibonding orbitals, the bond order is equal to 2 minus 0 divided by 2, which is equal to 1. This shows that there exists a single covalent bond between two hydrogen atoms. The hydrogen molecule is diamagnetic in nature, as no unpaired electrons are present in its molecular orbitals. Now let us discuss the bonding in a helium molecule. A helium atom has 2 electrons in its 1s orbital. Hence, the number of electrons in a helium molecule is equal to 4. These electrons occupy the sigma 1s and sigma star 1s molecular orbitals. Hence, the electronic configuration of a helium molecule is sigma 1s2, sigma star 1s2. Now, from the electronic configuration of helium, we can easily derive the bond order of the molecule. As the number of electrons present in both the bonding orbitals and anti-bonding orbitals is 2, the bond order is equal to 2 minus 2 divided by 2, which is equal to 0. This proves that a helium molecule is unstable and therefore does not exist. Similarly, beryllium molecule with an electronic configuration of sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and a bond order of 0 is considered to be non-existent. Now let's see the bonding in a lithium molecule. A lithium atom has an electronic configuration of 1s2 2s1. Thus, there are 6 electrons in a lithium molecule. The electronic configuration of a lithium molecule is sigma 1s2, sigma star 1s2, sigma 2s2. This configuration is also written as kk sigma 2s2, where kk represents the closed K-shell structure sigma 1s2, sigma star 1s2. As lithium has 4 electrons in its bonding molecular orbital and 2 electrons in the anti-bonding molecular orbital, the bond order of lithium is calculated to be half of 4 minus 2, which is equal to 1. From the bond order, it is clear that lithium is a stable molecule, and as no unpaired electron is present in its molecular orbitals, it is diamagnetic in nature. This diamagnetic lithium molecule is found to exist in the vapor state. Now, we'll see the bonding in another diatomic molecule, carbon. An atom of carbon has an electronic configuration of 1s2, 2s2, 2p2, which makes a total of 12 electrons in a carbon molecule. The electronic configuration of a carbon molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, which can also be written as kk sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. The bond order of carbon can therefore be calculated as half of 8 minus 4, which equals to 2. In a carbon molecule, the 2 atoms have a double bond between them. Both the bonds are pi bonds due to the presence of 4 electrons in 2 pi molecular orbitals. A carbon molecule is diamagnetic, as no unpaired electron is present in its molecular orbitals. It is found to exist in the vapor phase. Now let's look at the bonding in an oxygen molecule. Two oxygen atoms combine to form an oxygen molecule. The electronic configuration of an atom of oxygen is 1s2, 2s2, 2p4, and hence there are 16 electrons in a molecule of oxygen. The electronic configuration of oxygen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1, which can also be written as kk sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py1. The electronic configuration of oxygen molecule is such that there are 10 electrons in the bonding molecular orbitals and 6 in the anti-bonding molecular orbitals. Thus, the bond order of oxygen can be calculated as half of 10 minus 6, which is equal to 2. Hence, the oxygen atoms in oxygen molecule are held by a double bond. It has been proved experimentally that it is paramagnetic in nature. This is due to the presence of two unpaired electrons in its molecular orbitals. Similarly, the electronic configurations of other homonuclear molecules such as boron, nitrogen, fluorine and neon are shown here, from which bond order and magnetic property can be calculated, as given in this table.